Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the traction drives, and we were also discussing about the speed time curve of a locomotive which is moving from one station to the other station. So, we will try to derive the expression for the distance as well as the drive rating for a locomotive which is moving from one station to the other station. Now, here is our speed time curve. We have constant torque, then constant power, free running, and then we have the coasting and we have braking. So, we divide this into various regions. This is A, then we have. So, what we do here, we approximate this to be a trapezoid. So, we approximate this curve to be a trapezoidal curve like this. So, we call this to be A, and then this is the B here, and then we have C and we have the D in this case here, and we call this to be, this we drop a perpendicular here, this we also drop a perpendicular here. So, we call this to be E and this to be F. So, this is the speed time curve. So, what we have done here, we have approximated the speed time curve to be a trapezoid, and we define alpha as acceleration, alpha as the acceleration. So, acceleration, and this has a unit which is kilometer per hour per second. So, alpha is acceleration. So, we have the constant acceleration here, this is the constant acceleration, and this value of the acceleration is alpha. And we have also the deceleration, this is the deceleration, and the value of deceleration is beta. So, beta is deceleration during the braking region, and this is kilometer per hour per second. So, we define this as the time t1 and this as the time t2 and this as the time t3 for which it is braking, and the total time is capital T. The total time of travel is capital T. Now, we have to find out the area under the curve to find out the distance. So, the distance travelled here is area under the curve. So, what is this angle? This angle is, this is the acceleration. So, we can say that what is T1? T1 is, we have the maximum velocity here which is Vm, Vm is the maximum speed, and this is given as kilometer per hour, and the time is equal to T1 is the time for moving from A to B or A to E. So, in that case this is Vm by alpha and the unit is second. This is what we have here, that Vm is the maximum speed in kilometer per hour. So, T1 is the time to complete the acceleration, which is Vm by alpha in second. What is T3? T3 is for which the braking is done and it is basically decelerating, and deceleration is basically beta here. So, what is T3 here? T3 is Vm by beta, this also in second. So, the d in this case is the area of the trapezoidal curve, This is in kilometer, is equal to Vm into half T1 plus T2 plus half T3. So, this is what we have here, and if we simplify this, this is equal to Vm by 2 into, if you take this 2 common here, half common here, it is T1 plus 2 T2 plus T3, that is equal to Vm by 2 into 2 T minus T1 plus T3. So, we will further simplify this one, because we know that T1 is V by alpha and T3 is Vm by beta. So, we can simplify this. So, distance is equal to Vm by 2 into 2 T minus Vm by alpha plus Vm by beta. So, this is the expression that we found here. So, Vm is kilometer per hour, but this is in second. So, we have to divide this by 3600 if you want to obtain the expression in kilometer. So, this is in kilometer. So, we also have to divide this by 3600 to get that into kilometer. So, 3600 into this. So, 1 by 3600. So, this will be in kilometer. So, finally, we get here Vm by 7200, 2 T minus Vm by alpha plus Vm by beta in kilometer, where T1, T2 and T are time in second. So, all these times are expressed in second and the acceleration is given in kilometer per hour per second. So, if you want to find out the distance travelled between the two stops, that is given as Vm by 7200 into 2 T minus Vm by alpha plus Vm by beta in kilometers. Now, we have to find out the drive rating, and for that we have to also find out the tractive effort. When the train is moving, what are the various component of tractive effort? In the steady state, that is train resistance. In the steady state, we have frictional force, internal friction, external friction and the wind friction. What about when the train is accelerating? The train will not only run in the steady state, but also accelerate from start to the full speed. Let us discuss about the tractive effort when the train is accelerating from 0 speed to certain speed. So, tractive effort and drive rating. So, what are the various component of tractive effort? The tractive effort has to perform the following function. What are the functions? To accelerate the train mass horizontally, it has to move horizontally, then to accelerate the rotating mass such as wheels, gears, rotor of the motor, rotors of the motors, etc. And to overcome the gravitational force in case of gradient, overcome the force due to gravity while moving up or down a gradient. And then of course, to overcome the train resistance. So, we call to accelerate the train horizontally, say for example, the tractive effort is F A1 to horizontal to accelerate the rotating mass such as wheels, gears, axles, rotors, etc. This we call as F A2, and to overcome the tractive effort due to gravity, let us call this to be F G, and to overcome the train resistance, let us call this to be F R. So, the total tractive effort is the summation of this all the components. So, the tractive effort is equal to F A1 plus F A2 plus F G plus F R. So, let us try to evaluate the various components of the tractive effort. So, the first thing is that we have to evaluate the tractive effort to accelerate the train mass horizontally. So, what is this tractive effort? F A1 is equal to 1000 into m into alpha 1000 by 3600, and that is in Newton. So, what is m here? M is the mass of the locomotive in ton, and 1 ton is 1000 kg. So, we have to multiply this with 1000, and alpha is acceleration, in kilometer per hour per second. So, if you want to convert into meter per second square, we have to convert kilometer into meter by multiplying with 1000, and we have to convert hour into second by multiplying that into second by multiplying the hour with 3600. So, F A1 is given by this. So, we simplify F A1 as 277.8 m into alpha, and the unit is Newton. or n. And then we have to accelerate the train mass rotating parts. So, tractive effort required to accelerate the rotating parts are the following. What are the rotating parts here? The rotating parts are primarily the wheels and the motors. So, we neglect the moment of inertia of the axles, which can also be clubbed with the wheels. Let us say Nx is the number of axles, Nx is the number of axles, and each axle has got two wheels. Each axle has got two wheels. We have axle's moment of inertia can be neglected, but each axle has got two wheels. These are the wheels and this axle. So, each axle has got two wheels, and N is the number of driving motors, number of driving motors. So, when the motor is driving the wheel, it is basically sitting on the axle, and this is our motor which is driving the wheel. So, we have two gears here, one is the motor side gear, other is the axle side gear. So, this is the motor. So, N1 is the teeth on the motor side gear, and N2 is the teeth on the axle side gear. So, we have the gear on the motor side and gear on the axle side. These two are, when the motor is rotating, it is driving the axle. And what else? We have the moment of inertia. So, this A, we have the ratio A is equal to N1 by N2, and that is equal to the wheel speed. The axle speed is same as the wheel speed. The wheel is connected to the axle, and this is the wheel speed divided by the motor speed. So, motor is not directly connected to the wheel, it is connected to the wheel through a gear, it is a fixed gear, and R is the radius of the wheel. R is the radius of the wheel, radius of the wheel. So, the wheel is having a radius. So, this is the radius R. So, each wheel has a radius. So, this is the radius in meter. Okay. And then Jw is the moment of inertia of one wheel, moment of inertia of one wheel, and Jm is the moment of inertia of one motor, the rotor of the motor. So, total moment of inertia of all wheels, total moment of inertia of all wheels is equal to, we have the Nx is the number of axles. So, we have the number of wheels is 2 into Nx, and each wheel has got the moment of inertia is Jw. So, this is the moment of inertia of all wheels. So, we call that to be J1 combinedly. Similarly, total moment of inertia of all motors, total moment of inertia of all motors is equal to N into Jm. Jm is the moment of inertia of one motor, and we call that to be, let us say, that we have to find out. the referred value we have to find out. So, the moment of inertia of the motors referred to the wheels, because the motors are sitting here, this is actually the motor. So, we have a gear in between the motor and the wheel. So, if we refer this inertia j, this is the inertia of the motor to the wheel side, it will be j w by j m by a square. So, the moment of inertia of motors referred to the wheels, to the wheel side, is equal to n into j m is the total moment of inertia by a square, and that we can call as j 2. So, we are doing the calculation at the wheel side. So, we are referring all the variables in the wheel side. So, this is j 1 and j 2. So, acceleration in meter per second square, acceleration in meter per second square, we have acceleration in kilometer per hour per second, that is this into 1000 by 3600, and acceleration in, since we have a rotating system, we have to convert that into radian per second square. So, we have to divide this by the radius of the wheel to r. R is the radius in meter, r is the radius in meter. Okay. So, this is what we have here. So, the tractive effort for driving all the rotating parts. So, tractive effort for driving or accelerating all rotating parts is equal to, we have the moment of inertia is given as j 1 plus j 2. So, it is j 1 plus j 2 into the angular acceleration, and the angular acceleration is alpha into 1000 by 3600 by r. So, this is alpha by into 1000 by 3600 into r, and that is equal to j 1 plus j 2 into alpha by 3.6 r. So, what about the total acceleration? The total accelerating force F A is equal to F A 1 plus F A 2. This is for the linear and this is for the rotational. So, that is equal to the linear acceleration is 277.8 into m into alpha, and the rotational one is j 1 plus j 2 into alpha by 3.6 r. So, which we can we can combine, and we can combine this and write down that 277.8 into m equivalent into alpha. So, what is m e? M e is the effective mass of the train, effective mass of the train, that is equal to m plus j 1 plus j 2 into 1 by 3.6 r. So, because of the linear acceleration and angular acceleration of the rotating mass, we can find out an effective mass which is higher than the actual mass of the train, which can be 10% higher. So, instead of m, we have to take here m e. M e is the effective mass which accounts for both linear and angular acceleration. So, this is for the acceleration of the train, and then we have to have the tractive effort to overcome the gradient. Tractive effort to overcome force due to gravity, force due to gravity. Usually the gradient is defined as gradient is equal to g in 1000 meter. So, what is the elevation in 1000 meter? So, this is the gradient g. So, let us say that we have a track which is an inclined track. This track is little inclined and our locomotive is moving here. This has to move up or move down. So, if it is moving up, we have this mass, in this case is mg. We have a component of the mass which is along this direction. So, this is the angle theta and this theta is same as this. So, this is our g and this is 1000. So, gradient is defined as the elevation in 1000 meter. So, this is our gradient which is defined in this case. So, we have to find out what is the gravitational force here acting. So, the gravitational force which is acting here Fg. So, Fg is equal to, first our mass is 1000 m and then we have to find out theta, and this is mg into Fg is equal to mg into sin theta, which is approximately equal to mg into g by 1000. So, mg into g, capital G by 1000. So, that is equal to 9.81 m into g, and this is in Newton. So, this is about the gradient which can be positive or negative. This is up gradient which is positive, the down gradient we have negative. And then we have the fourth part which is the train resistance. Train resistance. The train resistance is basically expressed as a function of speed, something like this, where v is the speed here. So, it is very difficult to estimate the train resistance. So, what we do here, we use an approximate formula. The approximate formula is the train resistance is taken as a function of the weight of or the mass of the train. The train resistance is usually much smaller compared to the acceleration of the train, the accelerating force of the train. So, we say that it is something like 20 Newton per ton. So, the train resistance is approximated as, this is difficult to estimate, So, we say that the train resistance is approximately equal to R into m Newton. So, where R is the train resistance in Newton per ton mass. So, this is the train resistance. So, what about the total tractive effort? The total tractive effort is equal to the accelerating effort plus the gradient plus the train resistance, that is equal to 277.8 me into alpha plus minus 9.81 m into capital G plus mr into Newton. So, this is the total tractive effort of the train. So, the train has got this tractive effort, and then with the effort of the motor, the train moves forward. So, if you want to calculate the rating of the drive, so we can do the following. So, torque at the wheel here, motor rating, so that the torque at the wheel is equal to R into Ft, and that is the torque here. So, the torque at the motor is the torque by the transmission efficiency in Newton meter. So, T m is torque per motor is given as the total torque by the number of motors, and that is equal to R F T A divided by the transmission efficiency into N, and the unit is Newton meter. So, N T or eta T is the transmission efficiency. So, this is the torque which is seen by the motor. So, we saw that when we evaluate the tractive effort consists of the accelerating effort, the effort to overcome the gradient, and effort to overcome the train resistance. So, if you want to find out the time to reach certain speed, we have to find out the tractive effort which is being seen by the train, and that is given by this expression. So, this expression is extremely important. So, we have to remember the expression and use this expression at appropriate places. Thus, in this lecture we have seen how to calculate the distance covered by the train and what are the various components of tractive effort, and finally, how to evaluate the torque per motor, which is the total torque by the number of motors. So, we stop here for today's lecture, and hopefully we have been able to touch upon the important topics in this course. So, thank you very much.